There is a star in the constellation Scutum, nearly 20,000 light-years from Earth, that should not be possible. Its name is Stephenson 2-18, and if the measurements are correct, it is the largest star ever discovered. Its estimated radius stretches to 10 astronomical units, roughly 930 million miles from its core to its surface. If you removed our Sun and placed this star in its position, it would not just scorch the Earth. It would physically swallow Mercury, Venus, Earth, Mars, Jupiter, and Saturn. Every inner planet and every gas giant you have ever learned the name of, gone, consumed inside a single star. At the speed of light, it takes 14.5 seconds to travel around our Sun. To circle Stephenson 2-18, it would take nearly 9 hours. Its volume is estimated at 10 billion times that of the Sun. 10 billion. But here is the problem. Stephenson 2-18 might not exist. Not because someone invented it, but because the star we described, the Colossus with a radius that dwarfs Saturn's orbit, may be a measurement that outgrew reality. And the object behind those numbers may have already died thousands of years before any human ever looked up. To understand why, you need to understand what happens when a star grows this large. Our Sun is stable. It has been burning hydrogen for 4.5 billion years and will continue for roughly another 5 billion. It is disciplined, efficient, measured in its consumption. Stephenson 2-18 has none of that restraint. With a surface temperature of approximately 5,300 degrees Fahrenheit, extraordinarily cool by stellar standards, its outer layers have expanded so far from the core that gravity can barely hold them in place. The star is coming apart. Stellar winds tear material from its surface and hurl it into space at one of the highest mass loss rates ever recorded for any red supergiant, the equivalent of several Earths' worth of matter, stripped away every single year. Not gradually, relentlessly. The star is wrapped in a thick envelope of dust and expelled gas, its own debris, glowing in infrared wavelengths like the fading outline of something already halfway gone. Imagine standing at a safe distance and watching. You would see a bloated, dim, crimson sphere, shimmering unevenly at its edges, its surface churning with convection cells spanning millions of miles. No sharp boundary, no clean surface. Just a gradual dissolve from star into void, as if the object itself cannot decide where it ends and the darkness begins. How does something this vast survive? It does not. Not for long. While our Sun will endure for 10 billion years, a star like Stephenson 2-18 burns through its fuel in mere millions, a fraction so small it is barely a rounding error on the Sun's lifespan. If the Sun's lifetime were a single year, Stephenson 2-18 would live and die in the first afternoon. That is not a biography. That is a countdown. But the sheer scale of this star is not even the strangest part of its story. The strangest part is that we are not sure the scale is real. The estimated radius of 2,150 times the Sun was derived from a combination of the star's brightness and its surface temperature. Both values depend entirely on one critical assumption: that we know how far away it is. We do not. The distance to Stephenson 2-18 carries an uncertainty greater than 50%. The star could be significantly closer or significantly farther than the estimated 20,000 light-years. If closer, it is dimmer and smaller than we calculated. If farther, it could be even more extreme. And there is a deeper problem. A growing number of studies now question whether this star even belongs to the cluster it was assigned to. Stevenson 2 is a massive grouping of red supergiants deep in the Scutum Centaurus arm of the Milky Way, one of the densest concentrations of dying giant stars in our galaxy. Stephenson 2-18 sits near this cluster, but its radial velocity, the speed at which it moves toward or away from us, does not match the other members. Several research teams now classify it as a field star, a solitary red supergiant that happened to appear in the same region of sky. If that is true, then every physical property we derived from its assumed distance, its luminosity, its radius, its volume, may be wrong. Imagine measuring the height of a mountain and declaring it the tallest on Earth, only to discover that the ground you measured from was never where you thought it was. And stellar theory deepens the doubt. The theoretical upper limit for the largest possible red supergiant is estimated at roughly 1,500 solar radii. Stevenson 2-18, at 2,150, exceeds that boundary by more than 40%. Either our models of stellar structure are incomplete, which is possible, or the star is not as large as we calculated. So what are we actually looking at 20,000 light-years away? Something is there, a massive, deeply reddened star, hemorrhaging material, burning hot in infrared. It is real. But the version that earned the title, the one with a volume 10 billion times the Sun, may be a product of uncertain data, a figure inflated by the very distance that prevents us from seeing it clearly. And there is one final layer. Even if every estimate is correct, even if Stephenson 2-18 is truly the colossus the numbers suggest, the light arriving at our telescopes tonight left that star roughly 20,000 years ago. When that photon began its journey, human civilization did not exist. No written language, no cities, no astronomy. The light crossed the galaxy in silence while we invented everything we have ever known. In that time, Stephenson 2-18, already unstable, already shedding mass at extraordinary rates, already deep into the final chapter of stellar evolution, may have reached the end. A star this massive is a Type II supernova progenitor. When the core finally exhausts its fuel, it collapses in seconds. The detonation that follows can outshine an entire galaxy. If you were on a planet within dozens of light years, you would not hear it. You would not have time to understand it. The radiation would arrive before the warning. That explosion may have already happened. The shock wave may already be expanding through a region of the galaxy we cannot see. A neutron star, or a black hole, may already be forming quietly where the largest star once stood. And we would not know, not for thousands of years. We are looking at a memory. We gave it a name. We measured it. We declared it the biggest. But the universe does not pause for us to finish cataloging it. What we captured was not a star. It was the light one left behind, still crossing the dark, arriving just in time for us to call it real.